Welcome back. Today we're going to take a look at improper integrals. In general, when I'm talking about an improper integral, we're looking at an integral of a couple of following options, following types. We might be asking about an integral which does something like this. Starts at some number and goes all the way to infinity. Right? So I'm asking for an area under a curve which might go from 1 or 2 or 10 or something all the way to infinity. So I'm asking for what seems like it must be an infinite area because the area never stops. I never stop at including more and more area. We're going to see some like this. We'll actually discover that this area sometimes might be infinite, but there are situations where the area under the curve is actually finite as well. We might see something which is analogous, only it's with a vertical asymptote instead. So we might go from the area that seems like it might be unbounded and infinite is this area that's getting closer and closer to a vertical asymptote rather than this horizontal asymptote of the x-axis. So before I do that, let's just notice that really I can add infinite number of things and get a finite number. Right, that can happen. I can add an infinite number of terms and get a finite number. That's sort of like what we're doing with our areas under the curve. We keep on adding more and more and more area under the curve, but we're going to end up with just a finite value. But this happens all the time. For instance, 0.1 plus 0.01 plus 0.001 plus 0.0001 plus forever on out. If I add all of these things up, I get 1 in every single place value, which is 0.1 repeating, which is actually 1/9. So I've added up an infinite number of things, and I get a finite value in the end. And so what it takes is the stuff that we add up gets small enough, fast enough. If that happens, then overall we'll get a finite value. Okay, so let's start with this. Let's start with this one. Let's look at f of x as 1 over x squared. It looks a lot like 1 over x does, only it comes down faster because I'm dividing by x squared rather than x. And let's go from 1 to infinity. Now let's ask ourselves, what is this integral from 1 to infinity of 1 over x squared dx? What is that area under the curve? Well, notice that this is going to be our key idea for all of these things. Integral from 1 to infinity of 1 over x squared. How can I approximate this? Well, I can get an approximate value for this if I integrate it from 1 to a million, or 1 to a billion, or 1 to a trillion. And if I wanted to get a better and better and better approximation, we're going to make this upper limit of integration bigger and bigger and bigger. But this is exactly what the notion of a limit is good for. So we're going to take the limit as c goes to infinity of the integral from 1 to c of 1 over x squared dx. This, without a limit, from 1 to c, just goes from 1 to c. So I get a finite area under the curve. And then I take the limit as that c value gets bigger and bigger and bigger. So let's see what happens algebraically if we try to evaluate that. It should be a limit as c goes to infinity of the integral from 1 to c of 1 over x squared dx. Now, if I didn't have that limit, again, at c, we think about this as just some number up here, if I found the antiderivative of 1 over x squared, we'd get negative x to the minus 1. and then we need to evaluate from 1 to c. If this were the area under the curve from 1 to 10, we would evaluate from 1 to 10. And then after that, we'll take the limit as c goes to infinity. So limit as c goes to infinity. Minus x to the minus 1, well, that's negative 1 over x. So that's negative 1 over x from 1 to c. The limit as c goes to infinity of, if I plug in c, I get minus 1 over c. And if I plug in 1, I get minus 1 over 1. When I plug infinity in for c over here, 1 over infinity, if I put infinity in the denominator blows up, this goes to 0. So plugging infinity in puts 0 here, and this is positive 1. So the limit as c goes to infinity of my area under the curve is 1, which is actually finite. So we say that this integral from 1 to infinity of 1 over x squared dx converges. This is our language. It converges if the area under the curve is finite. Let's look at another one. Integral from 1 to infinity of 1 over x dx. Not 1 over x squared now, just 1 over x. Our idea is going to be exactly the same. We're going to take a limit as c goes to infinity of 1 to c of integral of 1 over x dx. But that's the antiderivative of 1 over x is ln. So I get a limit as c goes to infinity of ln, absolute value x, evaluated from 1 to c. Really, our limit comes at the very end. So this is a limit as c goes to infinity. If I plug in c, I get ln absolute value of c minus, plugging in 1, ln absolute value of 1. Now ln of 1 is 0. Let's remember what ln looks like. This is what natural log looks like. And ln of 1 is 0. And what's ln of c as c goes to infinity? Well, this actually goes all the way up to infinity. Remember, this is the inverse function of e to the x. So if I took e to the x and flipped it over the line y equals x, I'd get this. There's no horizontal asymptote to this. It all goes all the way up. And so this is actually infinity, because this piece is infinity and this piece is 0. So the area under that curve of 1 over x from 1 to infinity is actually infinite. And so this integral, we say, diverges. So converge means that the area is finite. Things come together. Diverge, they go apart. The area is infinite. All right. How about this one? The integral from 4 to infinity. So that number 1 that we started with, that wasn't special. We just really could have started anywhere, and the same thing we would discover the same thing. Let's start somewhere else now. 4 to infinity, e to the negative x. Again, remember what e to the negative x looks like? It's e to the x, but it goes down rather than an exponential function that goes up. So here's e to the negative x. Now we're going from 4 to infinity. And we'd like to know, does this integral converge or diverge? That is, does it get a finite area or does it get an infinite area? And if it converges, what is that actual area under the curve? So as always, it'll be a limit as c goes to infinity of 4 to c e to the negative x dx. Limit as c goes to infinity of antiderivative of e to the negative x. Well, we've seen that a bunch of times. It'll be e to the negative x, but it'll be negative instead. And then we have to evaluate from 4 to infinity. And so this will be the limit as c goes to infinity. If I plug in, 4 to c, sorry. Plug in c and plug in 4 and subtract. So this is minus e to the minus c when I plug in c. And then subtract minus e to the minus 4. And then we have to take the limit as c goes to infinity. Well, and I plug infinity in, so let's simplify. Limit as c goes to infinity. If I simplify this makes a plus, so that's positive e to the minus 4. I'm just switching the order so the minus comes second, minus e to the negative c. All right, well this is just a number. E to the negative 4 is 1 over e to the 4, so that is what it is. That's just a number. What happens as c goes to infinity of e to the negative c? Well, we already drew the picture. Here's e to the negative x. As this goes to infinity, the values go to 0. So this goes to 0. And in fact, our limit is 1 over e to the 4. So it converges. Let's look at one more for now. Let's look at 1 over square root of x from 2 to infinity. As always, limit as c goes to infinity of integral from 2 to c. Now let's put this into an exponent. So this is x to the negative 1/2. Negative puts it in the denominator, 1/2 makes it square root. So limit as c goes to infinity. This integrates to x to the positive 1/2 divided by 1/2, which is multiplied by 2, evaluated from 2 to c. Limit as c goes to infinity of 2, when I plug c in, and 1/2 power is square root, so 2 square root c minus 2 square root 2. And then I need to say what happens as c goes to infinity. Well, as c goes to infinity, the square root of c also goes to infinity. Because if I take the square root of bigger and bigger numbers, I get bigger and bigger numbers. So this goes to infinity, and this is still just minus the square root of 2. But if I take the limit of this stuff as c goes to infinity, this is still just infinity, because I'm subtracting off a finite number from infinity. So I get infinity back, and the integral diverges. And that's a good introduction to improper integrals. So check out the homework from this section.